So we're talking about the chemical properties here. If you look at the chemical properties in the book, there are a lot of them, a long list of them. But what we're going to do is we're going to skip those, and we're going to break down the chemical properties into just 3 types. But you know, the list is not comprehensive. So, for example, if you have a reaction like this, it doesn't fall into one of their categories. And 2, the list is a little bit confusing. And so if you look at the categories of chemical reactions that they show in the book, and then you look at the first reaction here, it doesn't fit in one of those categories. The other problem with that list is they have combination reactions. Combination reactions are an A plus B style reaction. This A plus B style reaction appears to go here and here, but there's no connection between those 2 reactions. And so what we're going to do is we're going to come up with an alternate classification system. The alternate classification system is going to be 1, metathesis. I already talked about metathesis. Can somebody remind me what metathesis are? Well, I didn't. I wrote down metathesis on the board, but did anybody write it down? Nobody wrote it down on Thursday? No? You didn't get it?
It was during the lab?
During the lab, yeah. Did anybody write anything off the board in the lab? On the left side of the board, I wrote it, on the far, far left side.
Is it when they exchange the, like, when you write them down, they switch the ions? Like,
Well,
so
yeah, that's double replacement, if you're familiar with the double replacement, but I
Well,
called
like
it
the
something
ions,
else.
yeah.
Yeah,
The ions?
the ions. It
Right
has to,
there.
yeah, you're right, it has to do with the ions. It was
yeah,
called,
so like, if it's like, mercury 1 and then like beryllium, so it's beryllium is 2 plus and then mercury is like.
yeah, not that kind of thing. It's the cation and anion combination.
Yeah.
You know, we spent almost all of Thursday talking about metathesis, which I called favorable ion combinations. So metathesis are called favorable ion combinations. So I wrote this on the left side of the board and wrote favorable ion combinations underneath it. But we didn't talk about acid-base, nor did we talk about oxidation reduction. So on Thursday we talked about reaction type 1. But today we're going to go through all 3 reaction types quickly, and then we're just going to look at examples of this. So when we're looking at it, what's the driving force for chemical change? The driving force for chemical change is typically we look for going from less stable to more stable. You know, there's a driving force for in physics. You know, the driving force is we go from things that are higher in energy to things that are lower in energy. Not vice versa. So if you're worried about something falling on your head, that's good, but you know, you look above and make sure nothing's going to fall on your head if you're underneath shelves. But do you look on the floor and worry about things falling up? No. And so this is what drives chemical change. So if we understand what's driving the chemical change, this is simplified, of course. There's more to it than this, but you know, essentially this is what we're looking for. And so what types of things are stable? And so we want to go from more stable, or we want to form things that are more stable. So what types of things are more stable? Well, I wrote them on the board on the left side yesterday. I mean, not yesterday, but Thursday. One of the things that are stable is a precipitate. Right? Precipitate's an insoluble solid, so the lattice comes together, and the ions combine. So precipitate, and there are 3 things I listed on the board: precipitate, gas,
Energy.
it has to do with energy. The last one was stronger acid to weaker acid, and I wrote one little thing with the hydrogen ion combining with ammonia to form ammonium on that. And so that was just a brief review. So we're just reviewing stuff from Thursday here. But what we're going to do is we're going to just try to understand chemical properties based on these three. And so I'm just going to jump around and just hit the key points. Metathesis, acid, base, and redox. These are the three basic types of reactions. And so what we want to do with these three basic types of reactions is just predict potential products that could form from these three types. So the easiest way to learn this stuff is just to do a bunch of examples. So I signed a bunch of examples for homework. But what we don't want to do is we don't want to do this. We don't want to come up with 10 plus subcategories of reactions. If you look in your lab supplement, you're supposed to memorize a dozen different types. But the problem with that list is it's not comprehensive. If it stopped at a dozen, we'd be fine. Just memorize those dozen types of reactions, you're okay. But there are a bunch of reactions that don't go on that list. So what we need is we need a more general procedure for doing this. So rather than subdividing it, we just subdivide it into three broad categories: metathesis, redox, and acid base. And then we look at subcategories or different types of reactions within those subcategories here. And so this is quick because we're just going to go through it.
Is it still chapter 8?
Chapter 8, 9, and Chem Compact B and Chem Compact G all wrapped up together. That's what it is. So, you know, when we're predicting reactions, you know, it's good to be able to predict reactions, predict what's going to happen if you mix these two chemicals. But, you know, there are some assumptions that we have to make when we do these predictions. The assumptions that we have to make is, and these are the basic assumptions, that we're dealing with fairly high concentrations. You know, if we're dealing with extremely low concentrations, then what we predict might not happen. And likewise, if we're dealing with extremely high concentrations, then we might get other things happening as well. And so what we have is this. This is a special concentration unit. And this just tells us the composition. Usually gas and liquid mixtures. This capital M stands for something called molarity. We'll talk about this later, but you know, this is one of our basic assumptions: is we're dealing with reasonable concentration and reasonable pressures. If we start dealing with extremely low pressures or extremely high pressures, then our predictions might not come out. And so all you have to know, you know, the take-home point of this is that, you know, when we make these predictions, we have to constrain ourselves a little bit. If we open it up, then, you know, we have to worry about other factors impacting this. All right, so there are different predictions here. This is what we call a double replacement type reaction. This is an AB plus CD type reaction. AB plus CD, we just switch the anions in C, and so, or cations, either way. So if we switch the cations here, we have B, what is that? AB plus CB plus whatever. And so we just move the silver with the chloride and the hydrogen ion with the nitrate to form silver chloride and nitric acid here. And this reaction does occur under reasonable concentrations, but under very dilute concentrations it doesn't occur. And so these are just examples of where, you know, we have to watch out. I made a typo here. This is not supposed to be PbCl2. This is supposed to be PbOH, OH2. What is this one? It's like 14. This is a typo here. And the other basic assumption is these are what we call thermodynamic driving forces. Thermodynamic driving forces don't tell us how long it takes. You know, some of these reactions can be very slow. One of the reactions that we predict to occur is the conversion of diamond into graphite. Graphite is thermodynamically more stable, and so it's lower in energy. Diamond is higher in energy. So if diamond's higher in energy, graphite's lower in energy, then it should fall down to graphite. But the problem is it takes too much energy to break all the bonds in diamond to rearrange them to form the more stable bonds in graphite, and so it's just not feasible. And so what we have is we have something called kinetically stable but thermodynamically unstable. That is, you know, there's no way diamonds are going to decompose into graphite in your lifetime. And so, even though we predict it's unstable, even though we predict there's a reaction, it doesn't necessarily happen. And so these are two little caveats. So when we predict reactions, we can't say, you know, with 100% certainty that this reaction is going to occur because we aren't considering all the factors that happen. And so, you know, the take-home message, there's a lot of detail on the slide, but essentially the take-home message is we make some basic assumptions, which means that sometimes our predictions are off because either our basic assumptions are off or we're not, you know, using it. And so you can't use these blindly. For example, you know, when I was taught chemical reactions, I was taught, okay, this does not happen, right? This does not happen. So I never considered that particular reaction to occur. But when I got to higher chemistry classes, I had this preconceived notion in my mind that this reaction doesn't occur, but it can occur under different conditions. I was never told about different conditions. And so I just memorized certain things that turned out to be inaccurate. And so, in other words, you have to have some flexibility. Okay, now, what we are going to do for these is this. Metathesis, we need to find favorable ion combinations. What are favorable ion combinations? Precipitate, gas former, and stronger acid and weaker acid. And we'll talk about each of these. However, there are some species that participate in metathesis reactions that don't consist of ions. One of them is ammonia. Does ammonia consist of ions? No, but why would I even consider ammonia in metathesis reactions? Because metathesis deals with ions. Ammonia is a molecule, it's a molecular compound. And so why is that? Did anybody catch that on Thursday?
Because it's a strong acid.
No, ammonia is what we call a weak base. We'll talk about electrolyte later, but electrolytes are ions, salts, ions, basically, that's all electrolytes are. And so normally we don't think of ammonia as being an electrolyte because normally ammonia doesn't consist of ions, it consists of molecules like water. Would you consider pure water to be an electrolyte? No, you add salts to water to make an electrolyte, right? Those salts make ions. Those ions are electrolytes, what we call electrolytes. And so ammonia, can somebody remind me why we would even consider ammonia in metathesis reactions when metathesis deals with ions? This is, you know, this is where, okay, because I told you the things are going to start to pile up. This is where I lose a lot of people. Around here is when people start to fall behind significantly. And then it's hard to catch up. But you want to keep, you know, try to keep on top of it and reviewing this stuff because the attrition, you know, that is, you know, well, the reason ammonia is considered in these is because a little bit of ammonia reacts with water. A little bit of ammonia reacts with water. And what happens? Well, the ammonia can react with a little bit of water to form a little bit of ammonium ions and hydroxide ions. This is where water is what we call the acid. The acid is going to give up an H plus to this. This is called the base. I wrote this on the board the other day. I'm not sure if you wrote it down or not. But watch out because some of the lab material, like the nomenclature stuff, even though it's lab, you know, it's correlated with lecture material. So some people just kind of ignore the lab, but a little bit of ions are formed. And so what we call this is, we call this like a weakly electrolytic solution. If electrolytes are salts dissolved, then a little bit of ions are formed, so we call it a weak electrolyte. This is a weak electrolyte. It's a weak electrolyte because a little bit of salts are formed, these ions, you know, weak electrolyte. Whereas a strong electrolyte would have lots of ions, like salt, you know, salt has got lots of ions because the lattice is completely torn apart and we form a lot of ions. That's a strong electrolyte. Whereas there are some things that don't get torn apart. Like ammonia does, but let's say sugar. Does sugar form electrolytes in water? No, sugar does not. And so sugar is what we call a non-electrolyte because sugar does not split up into ions in water. So we have strong electrolytes like salt, table salt, weak electrolytes like ammonia, and non-electrolytes like sugar. Sugar water is a non-electrolytic solution. And so we consider ammonia, whereas sugar water, we would never consider sugar water for metathesis because sugar does not form ions. So in order to understand what favorable ion combinations are, we need to know the solubility rules. And so let's review the solubility rules. I'll start off. Group 1 and ammonium are all
Soluble.
okay. Then what do I look at?
Group 2, right?
Well, then I look. Well, this is the cations. Then I look at the anions. Which anions do I look at first? Not group 2 because I'm done with the cations. Now I'm on the anions.
Chlorate.
Chlorates,
Nitrate.
nitrates,
The other one,
C2H3O2 minus is called acetate. R,
Soluble.
okay, then what?
Chlorine. Chloride.
Chlorides,
Bromide.
bromides, iodides, are,
Soluble.
except,
Silver. Mercury and lead.
oh good, that's from memory, that's good. And then what?
Sulfate.
Sulfates,
Those are soluble.
those are soluble except for,
Silver, lead, mercury, and more.
silver, lead, mercury, calcium. Just go down the list. Calcium, underneath calcium, strontium,
Barium.
and barium. That's a good start. You know, officially you're supposed to have that memorized by the next test, which is next Thursday. Yeah. So you still have time to get it down. And then after sulfates, we look at the mostly insoluble, starting with hydroxides. Good. Hydroxides are insoluble except for group 1,
And
ammonium, and not silver. Calcium, strontium, barium. And then after the hydroxides, you look at the sulfides, which are insoluble except for group 1, group 2. Let me finish it off for you guys. And then we look at the phosphates, carbonates, and chromates, which are all insoluble except for group 1 and ammonium. And so we know those are favorable ion combinations. They're favorable ion combinations because the ions come together to form a lattice, which ends up precipitating. And so those are good. And then we look at stronger to weaker acid. And we have this chart. This chart is in the supplement. And so if we look at the stronger to weaker acids, we're just looking at this one. This chart we don't have to memorize except for the 7 strong acids. There aren't just 7. There are more than 7 strong acids. But we need to memorize the 7 common strong acids. What are the 7 common strong acids? Let's start off with the first one. At the top is perchloric, hydroiodic, hydrobromic, hydrochloric, chloric, sulfuric, and nitric. If we memorize those and we see another acid, we can assume that other acid is weak, or weaker. And so, for example, phosphoric acid. Phosphoric acid is not one of the 7 strong, therefore it's a weak acid. And then we don't have to memorize this, although you'll see a pattern. Once you look at this enough, you'll see a pattern to this. But we're just going to use the chart. The chart's typically going to be given, for a test. Uh-huh.
On some of the formulas and stuff, how come it's not listed like for trial?
Trichloroacetic acid.
Yeah, how come it's like CCOO instead of?
Yeah, this is the way you write it in organic chemistry. COOH is what we call an acid group. Technically, it's carboxylic acid group. And so all of these acids, like acetic acid, formic acid, etc., butanoic acid, which is stomach acid, all those acids have the COOH group. In organic chemistry, this is called a functional group, so it's easier to see the structure of this written in this form. This type of formula is called a condensed structural formula. And so when I look at this formula, I can visualize how the molecule is put together. Whereas when I look at H2C2H3, there's two ways for writing acetic acid. This is our way. Our way is HC2H3O2. But if you're an organic chemist, you would write it like this because it's just much more informative to write it like this. Both of these represent the exact same molecule. But this is what we call condensed structural. So when you look at the formula, you can visualize the structure, right? And structure is very important. Composition, structure, and properties. This is what we care about the most. So if you look at this, this tells us nothing about the structure. One thing it does tell us, it tells us that out of the 4 hydrogens, they aren't all the same. That's one thing it tells us because of the way it's written. If this were written as a true molecular formula, we'd combine all 4 hydrogens here, and then you have no clue. The difference is they're trying to separate this so that they are showing that this hydrogen's different than the other 3 hydrogens. And so structurally, this hydrogen is different. What is different? This hydrogen is bonded to an oxygen. The other 3 hydrogens are bonded to a carbon, which changes their properties significantly. In fact, they're so different that we call these non-acidic hydrogens, and this is an acidic hydrogen. So this is called a monoprotic acid. Even though it has 4 hydrogens, it's called a monoprotic acid because only one of the hydrogens, one of the protons, is acidic. But that's more structural stuff we'll talk about later when we look more deeply at the structure of these things. Because if you look at the structure, you should be able to understand some of the properties of this. And so the organic chemist, this is the way you write it because it's obvious what the structure is based on that. And so that's why. And it's tricky, to us, we look for an H. All acids start with an H. But it doesn't matter to an organic chemist. It doesn't matter where it is. As long as they see this, they know it's an acid. And so you don't have to. It could be on the left. It could be on the right. It doesn't matter because.
So as long as there's just an H and then a non-metal acid.
Well, for us, we just look for an H. If you look at our book, if it begins with H, it's an acid. This is to make your life easier. But when you progress in chemistry, it doesn't have to be. But for us, we'll just take it. If it begins with H, it's an acid. If it doesn't, it might be, it might not be, but for sure, if it begins with an H, we're going to call it an acid. Okay. Well, we got to see how we're going to do this. I'll show you how we're going to use this in a little bit, but that's what we call the acid strength. So normally we look at the strongest acid. What's the strongest acid? Perchlorate. What's the weakest acid? The weakest acid is at the bottom of the list here, and it's actually methane. Methane is even considered an acid. This methane that's coming out of the gas jet, we don't normally consider an acid. That's why it's at the bottom. The only way you can get methane to react as an acid is if you have like a superbase reacted. But superbase is very unusual. This is what the Professor George Olah at USC won the Nobel Prize for. He won the Nobel Prize dealing with superacids and superbases, acids and bases that are way beyond what we have on this chart here in terms of strength. Those can do different types of reactions. So we're going to look at this list more later. I talked about only one gas former on Thursday. Do you remember which of these is a gas former? That we talked about on Thursday?
Sulfuric acid?
Not sulfurous, carbonic acid. What happened to carbonic acid? Because hydrogen ions like carbonate ions. They'll combine. When hydrogen ions and carbonate ions combine, they form carbonic acid. But carbonic acid, is it stable? No, it's unstable. Carbonic acid decomposes into, anybody write it down? Carbonic acid decomposes into water and CO2. And so this is something that people just memorize this. This is the most common by far. So if we have hydrogen ions, we take two hydrogen ions, combine it with a carbonate ion, then this doesn't precipitate necessarily, it forms carbonic acid. The carbonic acid in turn decomposes into water and CO2 gas. The CO2 gas effervesces. Well, it turns out that carbonic acid is not the only unstable species that forms gas. Sulfurous acid does the same thing, except sulfurous acid is going to form, what do you guess? Water and sulfur dioxide, not carbon dioxide. Sulfur dioxide is poisonous. Ammonium hydroxide is an unstable combination. Here, we see ammonium hydroxide, but it's not so stable. It's going to go back to ammonium water. But what happens is there are always collisions because there's always kinetic energy. And if a collision happens, a violent collision happens between these two, we're going to generate more ions. Yeah. And so, yes, it is unstable. It will decompose into ammonia. Ammonia is normally a gas in pure form, but it's quite soluble. Some things, like if you have hydrogen ions and sulfide ions, watch out. And whenever you have hydrogen ions and sulfide ions, it forms H2S directly, which is hydrogen sulfide, which is a toxic gas. If you have hydrogen ions and cyanide ions, hydrogen ions and cyanide ions love each other. They combine to form hydrogen cyanide gas. Hydrogen cyanide gas is lethal. Very dangerous. And so you never mix acid, H+, with salts containing cyanide. You never mix acid, H+, with salts containing sulfide because you're going to kill yourself. Unless you do it in what's that safety equipment called? For fumes and gases? Is that box? What's that box called? The hood, yeah. We call it the fume hood. If you did it in the fume hood, you're safe. Well, that, even though I say that, and warn people about the safety, in Chem 1B, when we used to do this, every semester somebody would mix acid with sulfide ion and generate hydrogen sulfide gas. You know what hydrogen sulfide gas smells like? Rotten eggs. It's because that's the rotten egg gas. And so the whole lab fills with rotten egg gas, and we have to evacuate the lab because it smells so bad. That happened every semester.
Is that what some of those stink bombs talk about that?
Stink bombs, actually, maybe, but I don't think so because it's too toxic. H2S is toxic at the part per billion level. You could die. Part per billion level is nothing, And the other thing about H2S is it does this. It overloads your olfactory sensors. So basically they become saturated. And so you detect it only for a short period of time, after which you become desensitized to it. And this is why there are so many deaths with H2S, because people don't smell it anymore. They smell initially, then the smell goes away. What they don't know is that their olfactory sensors have been wiped out, basically, and they can't smell it anymore. And they stay in the room. And this is why immediately we evacuated the lab, so people could clear out their nose and then come back in, because we don't know, after a few minutes, you might not smell it.
Is it permanent damage?
No, it's not permanent damage, but it'll give you a headache for sure. But if you're doing it every day, like it's your job, then it could lead to chronic damage. All right, so what we're going to do is we're going to look at a typical metathesis reaction. Here. And so this would be a typical question that you'd see. What happens if you mix calcium carbonate with sulfuric acid? So if we mix calcium carbonate, well, first thing we got to do is, what is the formula for calcium carbonate? Good, CaCO3. Now, what is the formula for sulfuric acid? HSO4? Close, but close. It's H2. It's H2 because sulfate's a 2-. So we need 2 hydrogen. Now, sulfuric acid, is that a mixture or is that pure? It's a mixture with sulfuric acid and water. And so there's water around, and so we call it AQ. Now, calcium carbonate, if there's water around, is calcium carbonate soluble or insoluble? So phosphates, carbonates, and chromates are all insoluble except for group 1 and ammonium. So this is not one of the exceptions. So this is insoluble, so we call it solid. And so this is like limestone. You know, does limestone dissolve in water? No. Okay, now what we do is we try to figure out what ions, you know, what are the ions here and what type of ion combinations do we have? And so the ions that we're working with are the calcium ion, the carbonate ion, the H+ ion, and the sulfate ion. Even though I have 2 H+, I'm just going to write 1 H+ because we're just looking at favorable ion combinations. And so we look, first, do calcium ions like sulfate ions?
Yes.
The answer is yes. Calcium ions like sulfate ions because
They're both 2 charged.
yeah, they're both 2+ and 2-. Now, the question next is this: is this a precipitate or not a precipitate? Because if it's not a precipitate, then they're going to just stay in solution and they're going to stay away from each other. If this is a precipitate, they're going to come together and form a lattice. Are they going to come together and form a lattice? Or are they going to stay separate? Yeah, they're going to come together because sulfates are all soluble except for silver, lead, mercury, calcium, strontium, and barium. So calcium is one of the exceptions. It's an insoluble salt. And then we look, do hydrogen ions like carbonate ions?
No.
Yeah, it forms carbonic acid. So hydrogen ions do like carbonate ions. We need 2 of them to form carbonic acid. But we know something about carbonic acid. Is carbonic acid stable? No. It's going to decompose into H2O liquid plus CO2 gas. Okay, so what we do is we look, you know, is this reaction going to occur? And so we need to determine driving force. We need to see if a reaction occurs. And so driving force is this. We want to go from something that's less stable to something that's more stable. More stable things would be precipitate, gas, and weaker acid. So the first thing we'll look at is precipitate. And so we got to go back to the solubility rules, and we see there's a precipitate here. And so normally if we get a precipitate, then we say that's a driving force. However, we have a problem here because, and this is the reason I wrote the little asterisk here. Note, we're sacrificing one solid to make another solid. So precipitation at the expense of calcium carbonate solid. And so what we need to do is we need to figure out which one is the more stable precipitate. Need to determine which precipitate is more stable. Why do I call the calcium carbonate precipitate? Because what we do is we're looking at this. We're looking at competing reactions. One reaction is going forward here. Because we want to go downhill, right? And so if going forward is downhill, that is, this is more stable, then that's good. But what if going forward is uphill? If going forward is uphill, then that means these are less stable, right? And that, therefore, if we reverse this, that is, if we were standing over here, we'd go downhill in the opposite direction. And so we call this favorable in the reverse direction, unfavorable in the forward direction. In other words, what we're seeing is which side is more stable. Is the product side more stable or the reactant side more stable? And that's going to dictate which way we go. So it's like a two-way thing, you know? It can go either way. And so this is why I'm meaning. Because if we go backwards, then calcium carbonate is precipitating. If we go forward, then calcium sulfate is precipitating. And so which one is more stable? Well, how can you tell about stability? What clues will give us stability about the lattice? One clue is the charge. You know, the higher the charge, the more stable. But when you look at the charges here, both of these are +2, both of these are -2. And so the next thing we'd look at is size, you know, but how does carbonate compare to sulfate? It's tricky, right? And so rather than trying to figure out it theoretically, that is, rather than trying to figure it out based on this lattice and Coulomb's law, we could use instead some experimental data to tell us. One piece of experimental data is this. If the lattice is stronger, is it easier to melt or harder to melt? Harder. So if the lattice is stronger, it should have a higher melting point. The other thing that we could look at is this, you know, that is, both of these are what we call insoluble, but it turns out that even though they're insoluble, that doesn't mean that absolutely none of it dissolves. What happens is a tiny bit dissolves, because when I look at water, it turns out that all the water molecules at room temperature aren't moving at the same speed. You know, they don't all have the exact same kinetic energy. Some of the water molecules are moving fast. In fact, they're moving fast enough to evaporate off the surface. So even at room temperature, we have molecules that have enough energy to escape the sticky solution, the sticky water. Well, the same thing here. Sometimes there's a higher energy water molecule that hits and breaks off some of the crystal. And so even though these are insoluble, a tiny bit dissolves. And so that, you know, the solubility rules, there's a basic assumption with the solubility rules. Do you know what the basic assumption with the solubility rules is? Well, let's take a look and see. Because, you know, a lot of people don't bother worrying about the basic assumptions until, you know, and they think, okay, it's insoluble, it's 100% insoluble. And so we need to figure out what that basic assumption is. And so when we look at this, does it tell us what the basic assumption is here? I look at this and there's no footnote here or anything like that. And then I look through the text, you know, this is talking about this. It's talking about the simplified solubility rules, etc. I don't really see it there. And so I'm going to go back to where I saw the solubility rules before. I saw the solubility rules before in our supplemental section here. So let's find the supplemental section, solubility rules. Actually, I probably should look at the table of contents here. Let's see. Simplified solubilities and reactions 1. Simplified solubility rules. Right here, reactions 1. So let's go to reactions 1 here. Here. I'm sorry? This is reactions 1. This is the same solubility rules. This is from the Chem supplement. All right, it's not there either. And so I have to do a little bit more digging. But this is what it means. When we talk about solubility, we can talk about it quantitatively and qualitatively. And so if we take a look at solubility, is sodium chloride soluble?
Yes.
Yes, it's soluble. And so we say yes, soluble. Well, this is qualitative. Okay, if it's soluble, then that means it dissolves in water, right? So let me ask you this. Is it infinitely soluble? So for example, if I want the saltiest water in the world, I just keep adding more and more salt, and as much as I want will dissolve. Is it? No. In fact, it has a limit. And you know what that limit is? That limit is about 36, 37 grams. And so it's going to be less than 37 grams will dissolve per 100 milliliters of water. So if I have 100 milliliters of water, I can't put more than 36 grams in there. You know, if I try to put that 37 gram, it's not going to happen. The same thing with sugar water. Let's say, you know, I have a real sweet tooth and I want to put like 30 sugar cubes in my coffee. Am I going to be successful? No, but sugar is soluble in water, isn't it? Yes, it is. And so what we say is this. When we do qualitative solubility, this is what it means. If something's soluble, we say S. This is a different S. This S over here means solid. This S here just means soluble. And that means this. It means that greater than 0.1 moles of molecules, moles of formula units, moles of whatever, will dissolve per liter. Greater than 0.1. If we call it insoluble, then all that means is, well, it gets an I. If we call it insoluble, that means less than 0.1 moles will dissolve per liter. And then we have one more, which we call slightly soluble. Slightly soluble is SS, and that means about 0.1 moles of solid whatever it is will dissolve in a liter. And so these, where did I get these kind of numbers? The quantitative we just look up in the book, you know. Probably the easiest book to look up, or Wikipedia. Wikipedia will have this data. And so what we can say is this. We could say this. If it has a stronger lattice, will more dissolve or less dissolve? If it has a stronger lattice, less will dissolve. So there are two things we can look at from experimental data. One is the melting point. The higher the melting point, the stronger the lattice. Two, we could look at solubility. Not the qualitative solubility, we need the quantitative solubility, exactly how much it will dissolve, you know, or as precise, it's not an exact number because it's measured, but as precisely as possible how much will dissolve. And so if we were trying to compare, you know, if we're trying to compare calcium carbonate and calcium sulfate, let's take a look at the data on Wikipedia. Calcium carbonate, oops, switch over to the computer here. We look at calcium carbonate, this is a typical entry here. You know, limestone, it's the mineral, it forms the mineral calcite. Calcite's inorganic, it forms beautiful crystals like that, and also different shaped crystals as well. And then aragonite, have you heard of aragonite? Aragonite's the calcium carbonate in shells. Like lobster shells or whatever, abalone shells. Abalone shells are primarily aragonite. Pearls, marines. It has other names: calcite, aragonite, chalk, limestone, marble, oyster, pearl. Okay, let's go down the data here and let's take a look at the data. Okay, make a note of the melting point. The melting point for calcium carbonate is extremely high. You know, in calcite form is 1339 degrees C. Aragonite, wow, the melting point is quite a bit lower, 825. that tells me that the arrangement of the ions is different in aragonite than it is in calcite. And so structurally they're different, even though the composition is the same. And so, but we'll take off the calcite form here, 13, because the aragonite's a biological form. Okay, so it melts at 1339, and then what we're going to do is we're going to look at the solubility in the water. Even though we call it insoluble, 0.013, that is 13 milligrams of calcite will dissolve in a liter. Now, that's not much, right? And so for the most part, it's going to stay out of water, but a tiny bit dissolves. So make a note of these two numbers, about 1340 and about 13 milligrams per liter. Okay, now let's take a look at calcium sulfate. So calcium sulfate goes by other names as well. Plaster of Paris, gypsum, and then this. Where have you heard this one before? Dryerite. Did you hear that one before? Plaster of Paris, in the old days, they used to use this for casts, making casts for broken bones. Gypsum is mined, out of the earth. Dryerite is the trade name for what? The blue powder. What's it called? The blue powder. No, it's. I mean, what is it used as? Dryerite is a, or used as a. Well, it is anhydrous. CaSO4 anhydrate. This is anhydrous here. Gypsum is the hydrated form. This is gypsum. You can see gypsum's hydrated. So maybe this.
What is the stuff used in silica packets? Because, like, for photography, I've used a little silica packet.
Yeah, the silica.
But mine have, like, if it's when they need to, when you need to switch them, or if, like, they get wet, they turn, I think they turn blue or pink to tell you that you need to replace them.
Okay.
So is that the same stuff that's used in dryerite?
If it's though they have silica, which is also a. Well, the word I was looking for is desiccant or desiccator, but that it could be, but there's others, so I'm not
So they're not
positive.
just all that one?
Yeah. The reason you have to word it could be dryerite because if it turns pink, then it's bad. If it's blue, it's good.
Yeah, for sure.
Okay, then it's probably dryerite. It's a desiccant. Anyway, here are the numbers. What is the solubility? 0.21, 210. What is the melting point? 1460. 1460. Now, what do we have here? What was the other melting point? 1340?
1340?
Was it 1340?
No, I think it was 1339.
1339? Okay. And so this one has a higher, melting point, but it's more soluble. And so this one, we need to do more data. We need more data. The melting point doesn't quite do it, so what we do is do it off solubility because we're looking off precipitation. And so it turns out that calcium sulfate is more soluble than calcium carbonate. If calcium sulfate is more soluble than calcium, then this is favored.
Does that mean that the lattice, you said is it higher the melting point, the stronger the lattice?
The stronger the lattice, right.
The less will dissolve?
The
So
less that should dissolve.
which one has the stronger lattice? Because that one.
Calcium
higher
sulfate
melting.
has a higher melting point, so it has a stronger lattice. But there's one other factor we haven't, because I'm oversimplifying it. When things dissolve, there are other things that come into play. And the other things that come into play have been ignored right now. And so if we're looking at precipitation, then it is, it would be nice if both agreed, but both didn't agree. So what we're gonna do is we're just gonna look at the site really. I mean, this has a stronger lattice, but what's forming in water is more favorable. And so if the products are more favorable in water, then it's okay. But the end result is this. This need to determine which is more stable, but this is advanced topic. And so typically in Chem 4, what you'll see is you'll never see a solid on this side in this type of reaction. They're only going to use aqueous here. They're only going to use aqueous, and then you don't have to worry about it, right? They only use aqueous, you don't have to worry about it. But if we only use aqueous, then we're narrowing and becoming narrower and narrower in scope. In other words, there are going to be more things that we could potentially miss. And so what I did was, I put this in here, actually I put it in here because this is the Chem 1A slides, but this is advanced. And so this one we'll just leave as a question mark because, you know, are we going to be able to Google things? Are we going to be able to do this theoretically? Not really. And so the point of this is we only need one driving force. Only need one driving force. Do we have one driving force? Well, precipitation, I don't know. It doesn't look good, right? What other driving forces were there? And what were the other driving forces in metathesis? That is, what other things are stable? What other things are stable is gas formation and... Okay, so we have gas formation here, and so we say this is a driving force, gas formation. And so even though this precipitation didn't give it to us necessarily, the gas formation does. And since we have gas formation occur here, then yeah, then reaction should occur. And so only need one driving force. We have it here. But in this particular reaction, we actually have two that we can say. What's the other driving force that we can bring up? And that is this one. Sulfuric acid, is that one of the 7 common strong acids?
Yeah.
Yeah. Carbonic acid, is that one of the 7 strong common acids? No. And so what we say is that we're going from a stronger acid to a weaker acid. And that would be the other driving force. Stronger acid, which I call SA, stronger acid, SA, to weaker acid, WA. And so this precipitation was very tricky because we're sacrificing one precipitate for another. And so what we do typically is we just skip that and look for the other driving forces. If I have another driving force, that's good. That tells me the reaction is going to happen. If I don't have another driving force, then we have to investigate the precipitation more thoroughly, which is kind of beyond the scope of this class because in Chem 1A they've never put this scenario up. Okay, let's go on to another example here. But before that, we're going to talk about what we kind of visualize is happening here. Well, actually, let's just leave it. We're going to leave it like this right here. All right, we talk about strong, weak, and non-electrolytes. Strong electrolytes have lots of ions. And so, let's see. We can tell if we have lots of ions. Do you know if does pure water conduct electricity?
No.
No. But does tap water conduct electricity? Yeah, tap water conducts electricity quite well because of the ions dissolved, because of the electrolytes involved in there. And so we can see here, do you see this light bulb? This light bulb, we have 2 wires or 2 what we call electrodes stuck in here. And the only way that this light bulb can light up is if electricity is conducted through the liquid. And in this case, electricity is conducted through the liquid because there are dissolved ions in here. So we call that a strong electrolyte. Over here, when we look, the light bulb is completely off because this is what we call non-electrolyte. These molecules are CH3OH. Do you know what CH3OH is? CH3OH is methanol. And so this is a beaker full of methanol. It looks like water, but it's not. If I had pure water, it would do the same thing. It wouldn't light up because methanol doesn't break up into ions, nor does water. Over here, this is acetic acid. If I have acetic acid in here, then it turns out acetic acid, most of the acetic acid molecules stay together. And so this is an acetic acid molecule, acetic acid molecule, acetic acid molecule. But a few of them, about 0.1% of the acetic acid molecules break up into hydrogen ions and acetate ions. And so a small amount of ions is formed in acetic acid. And this is showing hydronium here rather than H+. It's acetic acid. That's a weak electrolyte.
If the light bulb wouldn't light up with water, why is water such a good conductor of electricity?
If you use this water, it's a great conductor of electricity. You got to watch out for electrocution. If you use this water, it's not.
So if you were like in a pool and lightning struck the pool where you were in that water, you'd be fine?
If you're in a pool and lightning struck, lightning has such high voltage, you got to watch out because lightning could break down water and cause it to conduct. And so, if you were in a pool with this kind of water, you'd be a lot safer than a pool with this kind of water here. A lot safer. And so this water doesn't conduct electricity. Did I tell you when I was at UCLA, I used ultra high purity water in the psychology building. Do you know how we measured the purity of it? We looked at the electrical resistance. It's quick, easy. We looked at the, and they measure electrical resistance in ohms. And so I always check the water. If it's measuring in the mega ohm region, then it's like it conducts electricity as good as like rubber. You know, rubber doesn't really conduct electricity. It's got mega ohm resistance. So that's what we're looking for. And so the water, as I was getting it from the tap, it was an insulator. It didn't conduct electricity. Okay, potassium sulfide and acetic acid, this is advanced. I'm going to skip this one. Advanced. Lead iodide and hydrochloric acid, this one's not. But I made a mistake though. We don't know, is that lead 2 or lead 4? And it's actually, that one's supposed to be lead 2 iodide. Lead 2 iodide and hydrochloric acid. And so let's see what happens with lead 2 iodide and hydrochloric acid. Well, first we got to write out the formula. So what's the formula for lead 2 iodide? Pb I2. And the hydrochloric acid? HCl. So what ions are we looking at? We're looking at the Pb2 plus and the I minus, and we're looking at H plus and Cl minus. And so we already have Pb and I. Well, actually, lead 2 iodide. And H plus and Cl minus. I did 3 advanced problems in a row. This is advanced also, but it's all right. Let's try. And so what we're going to do is we're going to see if we can form better combinations. And so rather than Pb2 plus with iodide, we'll try Pb2 plus with Cl minus. And so the easiest way that people do these types of reactions is like this. If I want to see how they'll do with the other ion, I just switch partners here. And so what we'll have now is Pb with chloride instead. And so that's going to form PbCl2, and then we'll have H with I, and that forms HI. This is not balanced. And so all I did was I'm gonna switch the anions and see if I can come up with a more favorable ion combination. Now we know that chlorides, bromides, and iodides are all insoluble. And so this should precipitate. That should precipitate. But the problem is this. PbI2, is that soluble? Chlorides, bromides, and iodides are all insoluble. Are all soluble, excuse me, except for silver, lead, and mercury. So that's insoluble. So what do we have here? We're giving up one precipitate to form another precipitate. So let's see if the data is a little clearer on this. And so I'm going to take a look at the data here on Wikipedia and then try to compare the two. So I'm going to go PbI2, lead-2 iodide. And so let's take a look at its melting point. Melting point is 402 C. And let's take a look at the solubility. Solubility is 0.044 grams per 100 milliliters, which is 44 milligrams per 100 milliliters. And so let's remember the melting point 402 and then 44 milligrams. Okay, now let's go to PbI2. That was PbI2. Let's go to PbCl2. Go to PbCl2. Melting point 501. Solubility 501 tells us that lattice should be stronger, right? Harder to melt. But when you look at the solubility is telling us this is 10.8 grams per liter. The other one was 44 milligrams per. And so if that's 10.8 grams per liter, then per 100 milliliters, it'd be 1.08 grams. And so this one's more soluble. We need more data. So this is inconclusive here. So we don't know this one. So we aren't going to worry about that one. However, let's look at the other driving. Are there other driving forces that we can consider? Gas formation. Well, HCl and HI are both gases, so that's inconclusive as well. But they're soluble in water. What's another driving force? Stronger to weaker acid. And so HCl, is it one of the 7 common strong acids? Yes. HI, one of the 7 common strong acids? Yeah. And now which acid is stronger? Okay, so if we go back to this one, let's take a look. If we look at this one, it appears that HI is indeed a stronger acid than HCl. It appears that it is. And so stronger according to the chart. Stronger according to chart. But there's something called the leveling effect. And what the leveling effect says is this. Leveling effect. All strong acids have the same strength in water. So, if both of these are strong acids, it's a tie then. It's a tie. And so this one is a tough one to figure out because it's a tie.
So it's inconclusive.
I'm sorry?
So it's inconclusive.
Inconclusive, right. So, what we need to do is, okay, let's not do these, let's do simpler ones in which everything works out nicely. That one we could figure out, based on solubility. I'll tell you which one forms. The one that's less soluble. And so the one that was less soluble is PBI2. And so this one should be here. This side should be more stable. Okay, so we'll take a break here and then we'll look at some ones that are easier to deal with. And those are the ones in our book.